Hello viewers, let us discuss one topic entitled Modeling and Simulation of Isfet device. In general, modeling is a process by which the objects in the real world can be represented in terms of physical or mathematical equations and parameters. To form a model of a device in general, equations are derived from the qualitative understanding of the device that can best approximate the behavior or characteristic of the device. That is, equations derived must be based on qualitative theory. For an example, basis of well-known SPICE modeling, that is, simulation program with integrated circuit emphasis dedicated to semiconductor devices, which revolves around the creation of electrical models, is the concept of fundamental physics. To make it clear, let us consider the well-known drain current equations of enhancement mode MOSFET or E-MOSFET. These two equations are well known. Also, we have discussed earlier. One is drain current at a non-saturation region. This is drain current at saturation region. These are well known, where beta is a design parameter given by this expression, which is a constant. Now, as we all know that these equations have been derived by using fundamental physics theories. If we now perform experiments on a standard E-MOSFET, which you can purchase from the market, to find the output characteristic of the device, then it will be found that the characteristic curves satisfy the equations 2 and 3. And if it happens, then these equations are considered as the transport model of the device. Why modeling is important? Because modeling is important because it can give us knowledge about the device physics. Modeling also helps us to explain experimental data. Modeling also helps us to choose the parameters for high sensitivity and selectivity of the device. So that is why modeling is very important. And as far as Isfet modeling is concerned, it is worth mentioning that Isfet is a chemico-physical system, because Isfet has two parts. One is liquid part or liquid phase, other is solid part or solid phase. That is why it is a liquid part, it is associated with chemistry, and solid part, which is a semiconductor part, which is generally a physical part. That is why Isfet is a chemico-physical system. Therefore, even though many physical models have been developed in SPICE with the modifications over well-known MOSFET models, such SPICE models are not exact, as electrochemistry involved in the device are not included in the device model, and as a result, the chemico-physical significance was rather unclear. Electrochemical model is therefore regarded as the acceptable model as far as Isfet is concerned. Electrochemical model is generally developed considering all the chemical and physical parameters involved in the device activities. It can be developed by considering the theory involved in electrolyte insulator surface which is a chemical part, and insulator semiconductor surface, which is a physical part. Electrochemical model can therefore be developed by considering side binding theory, electrical double layer theory, pH dependent surface potential, threshold voltage, and current transport model. As far as side binding and electrical double layer model is concerned, we have discussed it earlier. Here, for example, suppose let us consider an amphoteric surface having only one type of site, A, denoted by AOH, in contact with electrolyte solution. This is the electrolyte solution. Amphoteric means it may show the behavior of acidic nature, it may show basic nature, or even it may show neutral nature. And the acidic and basic character of the neutral site can be characterized by generally two equilibrium constant, acidic constant and basic constant, which are generally in chemistry defined by equations 9 and 10. We have discussed earlier. From this side binding model, we get the expression for the parameter H plus S as this expression that also we have discussed earlier, denoted by equation 7. Here H plus S is the hydrogen concentration, ion concentration at near the insulating surface, represented by S. Here this hydrogen ion concentration in the electrolyte solution of which pH is to be determined. Surface potential model. Using side binding and electrical double layer model, we will get the surface potential expression as shown by equation 8, which is also known as Bausch's model because he has developed it. That also we have discussed earlier. Here beta is a dimensionless parameter that determines final sensitivity of the gate insulator and depends on surface hydroxyl group and surface reactivity. Beta is generally given by this expression, equation 9, where this Ns is the total number of surface site per unit area. CDL is the capacitance of the double layer in the electrolyte solution. And the value of pH at the surge neutrality point of the oxide surface, denoted by PZC, can be determined now using equation 10. So if we now perform an experiment on an Isfet to plot a curve Zinot versus pH, that is interface potential versus pH of the solution, then it will be found that curve, experimentally determined curve, will satisfy the equation 8. Therefore, equation 8 can be regarded as the model of the surface potential of the device. So actually two works are involved. First, you have to develop one mathematical expression based on qualitative theory of the device. And second, after formulation of this or after derivation of this mathematical expression, you have to verify it experimentally. If both agree, then your developed mathematical expression will be considered as correct. Otherwise, no. Threshold voltage model. This also we have discussed earlier. Threshold voltage of an Isfet device is given by this expression. Equation number 4. Here, this Zinot, the interface potential, can be mathematically expressed as shown in equation 7, where C is a constant given by this expression. Here all parameters are actually constant for a particular device. All parameters, E reference, it is a reference voltage which is kept constant. This is the solvent potential, which is also related with electrolyte solution, which is constant. And this is also the phi m, work function of the metal gate, expressed in electron volt, and Q is the electronic charge. Current transport model. It is the very important model, because ultimately in the device, as output, you will get current, because Isfet, it is an electronic device, transistor, so output is generally current device. So the drain current in linear and saturation regions can be modeled as this, already discussed. IDS equal to this. VDS is the drain to source voltage. VGS is the gate to source voltage. This is the threshold voltage of Isfet. And in the saturation region, it will be given by this. Here also, beta is a design constant, which is constant. Now, next part is after formulation of the mathematical expression to represent different parameters of the device related with the device, you have to verify it. How can we verify? For verification, we have to perform experiment on the device on which mathematical expressions have been derived. This is known as model validation. Any mathematical model that we have discussed, or any model that you have developed, or any model that you are going to develop, is basically a theoretical model, because it is based on some sort of scientific theory. Say, for example, based on physics theory. So after development, whether it is correct or incorrect, that must be experimentally verified for acceptance. This validation can be done as follows. Let us consider a surface potential model, which is defined by this equation. It is actually Bausch's model. Here, all values except beta is a sensitivity parameter obtained from literature survey. So from different literature, you will get the values of this Boltzmann's constant K, that is known value, T the absolute temperature at which the experiment has been performed, and Q is the electronic charge. PZC is the pH at the point of zero charge, which is actually known. And pH, here pH is the pH of the electrolyte solution, which is to be measured. Here, beta may be obtained from literature survey. The value of beta can be calculated using this relation, beta equal to this and delta equal to this. Here also, all values can be obtained from literature. In this way, the values of xi naught for different pH values can be obtained theoretically. So also you know that as far as threshold voltage of Isfet is concerned, threshold voltage of Isfet is pH dependent. That means that at different pH values, you will get different xi naught values. So first, from experiment, you find the threshold voltage of the Isfet device experimentally by plotting gate to source voltage versus IDS curve. For different pH values, you will get different interface potential xi naught. So you from this you make a table. And referring to the experimental part, xi naught being interface potential cannot be directly experimentally determined. For this, you first find the Isfet threshold voltages from experimentally determined transfer characteristic curves at different pH values using extrapolation in linear region technique as discussed earlier. That is what is this technique? That after plotting the VGS versus IDS curve, for each curve you have to draw tangent, but you have to draw tangent at a point where you will get the maximum slope. Then the tangent, the point at which the tangent cuts the VGS axis, that point will give you the threshold voltage of the device for a particular pH value. The values of xi naught for different threshold voltages of Isfet can be now experimentally determined using the equation 7, because C is constant. V threshold MOSFET can also be obtained for MOSFET device from which the Isfet has been fabricated. So for validation purpose now, you draw one pH versus surface potential curve, both for experimentally obtained values and theoretically obtained values, which is known as modeling. Curve obtained during modeling and curve obtained during experiment. Theoretical, after plotting, the theoretical simulated results should be in good agreement of the experimental results, and if it happens, then developed model can be accepted. Now, at this, what is the importance of this topic at this particular time? Because you see, at this pandemic period, this topic has importance because research works related to this area may be carried out from home. Why? Because only requirements are your knowledge for development of models and experimental results are required for validation. Only these two requirements are required. So for a particular device, the experimental results may be available in literature, and you may collect these experimental results through literature survey. Thus, you can pursue the research activity from home. However, in conformity with nation's mission, Atmanirbhar Bharat, if you want to link your research work with industry, or if you want to open startup program, it is advisable to fabricate the device on which you are going to perform experiment yourselves. And in order that you may acquire more knowledge on modeling and simulation area, some of our research articles published in well-regarded journals are given here. Thank you.